Okay, in this example, we're looking at two blocks on a inclined plane or on a ramp, and those two blocks are connected by a rigid string that is massless, running over a massless and frictionless pulley, right? So look, we got all these conditions here, right? So we don't want the string to have mass because we don't want it to have inertia and have that affect our accelerations, and we want the pulley to be massless so that it doesn't affect the tensions on either side of it. And we have a frictionless pulley because we don't want the pulley to slow down the motion. And okay, so two blocks, different masses, block reference to the incline. Oh, and one thing that actually isn't mentioned in the problem is that the incline is has no friction. Okay, so it's a frictionless incline. Okay. Okay, so let's think about our sum of forces. Okay, so I'm going to go through the steps for solving a force problem like this. So steps 1 and 2, draw free body diagrams and choose axes. Okay, and you might notice that no values are given in this problem. That's because we're just going to keep everything symbolic and just get an answer that would apply to any situation of two blocks, of any mass, any combination of two masses. Okay, so let's draw some force vectors. We're going to have a tension, right, pulling M1 up the incline. And there's going to be a tension that's affecting M2 as well. Okay, then we're going to have a gravitational force acting on both blocks, M1 and M2. Okay, so this is F. All right, here are both the gravitational forces. Okay, this one is G1 and this one is G2. Okay. All right, and then we also have a final force acting on M1 because it's resting on a surface, so we have the normal force. Okay, and the normal force is, by definition, always perpendicular to the surface. In fact, that's what the word normal means. Okay, so now that we have that, we're going to write our sum of forces. So step 2, write the sum of forces for both blocks. Okay. Okay, so what that's going to look like, well, we're going to have the sum F net 1 in x, F net 1 in y, and then we're also going to have F net 2, but just in y. And that reminds me that we haven't chosen coordinate axes yet. So what do we mean by x and y? Well, we can choose different coordinate axes for each free body. We have to be consistent with coordinates for a given free body. Since we have two free bodies, we can have two coordinate axes. So I'm going to choose a tilted coordinate axis for mass m1. And by tilted, I just mean that I want it to be parallel to the slope. Or I want the x-axis to be parallel and the y-axis to be perpendicular. And then for the hanging block, I'm simply going to choose a coordinate axis where positive y is defined upward. Okay? So the reason I tilted the coordinate axis here for mass m1 is because I want to have as few components as possible in my calculations. Had I chosen a non-tilted coordinate axis like this for m1, then I would have had components in the normal force and in the tension force. But by choosing a tilted coordinate axis, like I did over here, the only components are going to be in gravity. Okay, and we'll see that. Okay, so let's go ahead and start summing up our forces and thinking about what they look like. And we're just going to write everything completely symbolic, and then we'll incorporate the angle alpha in the next step when we expand our sum of forces. Okay, so in the x direction for block 1, okay, well, there's going to be the tension force, which points in the positive x direction, okay? And there's going to be a component of the gravitational force. Well, what do I mean by that? Well, let's zoom in a bit so we can see that component. Okay, so basically, if we look at our gravitational force here, right, and we consider the axis that we chose, then we can realize that there are two components of gravity. It makes a little triangle like so. Okay. and those components would be the x component of gravity and the y component of gravity. All right? And the x component of gravity points in the negative x direction. All right? Negative x. And so that means that it's going to show up as a negative in our sum of forces, which we'll get back to right now. Okay. All right. So let's take a look at that. So we have minus, all right, minus FG1x. Okay. And furthermore, there is acceleration in the x direction for block 1, which would be m1a. Okay. Now let's go to the sum of forces in the y direction for block 1, and that's simply going to be the normal force pointing up and the y component of the gravitational force, Fg1y, pointing down, the negative direction. And that's going to sum to 0 because there is no acceleration in the y direction for mass 1. And now if we look at the forces on mass 2, only in the y direction, we have tension pointing up and gravity, all of gravity, pointing down. And then that's going to equal the acceleration of mass 2. But mass 2, we're going to assume is accelerating down. Okay, so we're going to have negative m2a. Okay, so the reason for that is essentially that I'm having mass 1 accelerate up the incline, and I'm defining that as positive. And then if mass 2 is going to be accelerating down as a result of mass 1 accelerating up, then that's going to be in the negative direction. Okay, it's just important to be consistent with the accelerations, and that's yeah, especially in a problem like this. Okay, now I wanted to call attention to a couple of assumptions I made here. One is with the tension being equal, and the other is with the accelerations being equal. Okay, so quick note, put it over here, that Ft is equal on either side of the pulley because the pulley is massless. Because the pulley is massless, okay. So that's always the case for massless pulleys. Okay, and then the second note is that A1 equals A2 equals A because the string is rigid. Okay. Okay, so that's where those assumptions come from. So moving forward with the problem, step 3, we're going to expand our sum of forces. Okay, and by expand, I just mean write them with more information and include any cosines or sines where necessary with our components. Okay. All right, and okay, so I'm going to do that for the, basically, actually, I'm just going to do it for x and y of blocks 1 and 2 respectively. In other words, I'm just going to leave out the sum of forces for block y. So I'll say that right here. So this is going to not be necessary for a solution of solving for the magnitude of accelerations of both blocks. Okay, so right here, not needed for a solution. So the reason that the sum of forces in y is not needed for the solution in this case is because it's a frictionless case. In general, the only time we're actually ever going to worry about an equation that involves the normal force is when we have friction, and that's when it's one of our steps for algebraic substitution or manipulation of our system of equations, and that's when it matters. But if there's no friction, like in this case, then it doesn't really tell us anything other than just that the normal force is equal to the y component of gravity, and that's the end of the story. But that we can't feed forward that information. All right, so let's look at the first one. Okay, so if we just look at the sum of forces in the x direction for block 1, we get the tension force, okay, and then the x direction of the the gravitational force. Well, that is going to be m1g, and then the question, is it cosine or sine? Well, it's sine, so it's sine of alpha. And so the idea here, if I was to zoom in, and if I will, I'll show you that this angle right here is alpha, okay? So this angle is alpha, the same alpha as this one here, okay? And we can think about the geometry for that, and we can also think that as alpha went to 0, right? If this was to shrink down, if it was shrinking and shrinking and shrinking, right, getting smaller, then we're going to have a case where as alpha approaches 0, the x component would also approach 0, right? Because then gravity would just become more and more vertical until it was entirely vertical at the point that alpha is 0. Well, that means we need a trigonometric function that's 0 at 0. Well, sine of 0 degrees gives us a value of 0 because the sine function passes through the origin. So you can think about it geometrically, or you can think about it with the limiting cases of the functions. Okay? Okay, and then that's going to be equal to m1a. Okay. All right, so that's our first equation that we included our components on. Okay, let's go to the other one we care about. And so then we have the tension is then to be equal or minus m2g, no components there, and it's to be equal to negative m2a. Okay. All right. And I'm going to put a note up here that I think that, because I included it here with the signs that, this one is positive and this one's negative. But I want to just make it clear on the figure that we're assuming, let's put it here, right? So this is acceleration. Okay, so I have acceleration going up this way and acceleration going down that way. Okay? So in other words, acceleration is positive when it's in those directions. Okay? So we'll say indicated directions of acceleration are for positive acceleration. All right, so if the acceleration is in the direction indicated, then we'll get a positive value. If the acceleration is in the other direction, then it would be negative, right? So then that would be a negative a. All right, so that's we're building that into the problem. So then once we get a solution, that's going to be symbolic because this is a symbolic example, and we're making sense of that solution. We can see, oh, well, if it's outputting a negative value, then the acceleration is going opposite of the direction we assumed. All right, so it's baked right into the way we set up our equations. Okay, so let's do a substitution and solve for a. All right, so we'll call that step 4. Solve for desired value. In this case, it's acceleration. So we're going to want to eliminate tension using a substitution. Okay, so I'm going to use the top equation to substitute in or solve for the tension, and then substitute that into the bottom equation. Okay. In other words, top equation is the m1 equation, and the bottom equation is the m2 equation. They both just really have their own equation because it's a frictionless problem. Okay, otherwise we'd have a little bit more to work with m1. Okay, so let's move on. So then we're going to have t is just going to equal m1g sine alpha plus m1a. Okay, and then we can go ahead and substitute that in. Okay, so then we're going to have m1g sine alpha plus m1a minus m2g equals negative m2a. Okay, and that was by substituting this in for that. Okay, and then just writing that whole equation. Okay, we're going to collect like terms and solve for a. Okay, so we want to get all of our a's on one side and our g's on the other. So what that's going to look like, I'm going to put the a's on the left-hand side. So we're going to have m1a plus m2a is going then to equal m2g minus m1g sine alpha. And then when we solve for a, we're going to get, and we'll factor out a g on this side of the equation, on the right-hand side, m2 minus m1 sine alpha, and then all divided by the sum of the masses m1 plus m2. Okay, and we don't have any values to plug in, and so we can just leave this entirely symbolic, and that's our final answer. I just want to speak to the answer briefly and point out that it gives us the results that we would expect, that we have that the acceleration is positive if m1 sine alpha is less than m2. So I'll put that over here. Okay. So acceleration is greater than 0 if m2 is greater than m1 sine alpha. Okay, so it's going to accelerate in the direction we assumed. Now, if m1 sine alpha is really large, then that's going to cause the whole system to actually go the other way. In other words, if m1 was really big, then it's actually going to pull m2 up, and that could certainly happen. And then we can see what value that would take, right? It would simply be that m1 sine alpha would have to be bigger than m2. Okay, so changing the angle then would change the how big m1 has to be in order for that to happen. If we look what's going on in the denominator, basically the whole system is slowed down by the total mass. And in many of these problems where we are dealing with free body diagrams and one mass pulling another due to its inertia and it being influenced by gravity, we find that the final acceleration of any of the free bodies in the system always has the total mass of the system in the denominator, because that's the sluggishness of matter. The system itself is dependent on its overall mass to determine how fast it moves. A really big system, even with a big difference between m2 and m1 sine alpha, would still move slower than a smaller system with the same difference between the relative masses, because it's a larger, more sluggish system. It has more inertia. It's harder to get going. Also, the other big note I want to mention here is that this result is the same as an Atwood's machine if alpha equals 90 degrees. Okay? Well, if you think about it, since this is a frictionless incline, if we were to make alpha 90 degrees, right, if it was to go all the way up there, well, then alpha just becomes a wall. And since it's frictionless, it's not actually doing anything on the system. And so then it might as well just be air. And then we just have two blocks hanging on either side of a pulley, which is, by definition, an Atwood's machine. So a result makes sense. Hopefully you find it interesting. And thank you.